Let's continue our discussion for particle kinematics. We will finish this chapter in this video. So, particle kinematics, last time we have seen normal and tangential components whenever there is a curvilinear motion. Now we will continue our discussion about curvilinear motion with cylindrical components or polar coordinate system. We have different coordinate system depending on a problem that you use. So here you have rectangular coordinate system in which you have Cartesian coordinates, you have x-axis, we have y-axis, and then you can plot point P as pxy from x distance from this y-axis and y distance from this x-axis. So that's your point pxy. That's your rectangular coordinate system. There is another system known as cylindrical coordinate system or polar coordinate system. So let's assume that this radius is rotating like this. In that case, if you have a rotation, it's a good idea to use polar coordinate system, in which instead of x and y, what we have is r and theta. Here, for rectangular coordinate system, we have I and j as unit vectors. In polar coordinate system, we will have, instead of I and j, we will have ur and u theta. So that's your unit vectors in polar coordinate system. So r is radial coordinates and theta is transverse coordinate. So if I tell you radius r, let's say 5 meters or 5 centimeters, and then theta is 60 degrees, you should be able to plot a point. The way I will tell you that, plot a point 3x, p34. So you will take this x is equal to 3, y is equal to 4, and you can plot a point. Same way, if I tell you theta is 60 degree, r is 4 meters, then you should be able to, from the 4 at 60 degree, you should be able to plot a point. So that's how it works, pr theta, pxy. For cylindrical coordinate system, here we use r theta. So respective points, let's say there is a point p theta r that is 4 and 60 degrees or 4 pi by 3, that's in radians. So 4 pi by 3, that's the point you have to plot here, and you will plot here. If that's the case, and what is the respective point in this system? So to calculate that value is that we will do p is x is equal to r cos theta, r is going to be 4, theta is 60 degrees, so r cos 60 will come here, and y I is equal to r sin 60, that's 4 sin 60, 2 by 3. So you are going to plot this 2 by 3, x is equal to 2, y is equal to 2 by 3, and then you can plot that point here. It will become p2 2 by 3 equivalence p4 60 degrees or p4 pi by 3. So that's the general idea how this rectangular coordinate system and polar coordinate system work, also known as cylindrical components. And then we are going to more concentrate on this part. Here the way we do ij, here we do ur and u theta. So keep that in mind. So just a recall, if it is rectangular components, if you are using regular Cartesian coordinate system, and let's say there is a particle traveling in a curved path, then the position is given, position r is given by this formula xi plus yj plus zk. We already did that, it's just a recall, xi plus yj plus zk. Then the velocity is nothing but dr by dt. So I'm going to differentiate this one with time, and then I'll get x dot I, y dot j, z dot k. That's x velocity, y velocity, and z velocity, and I, j, k are your unit vectors. And then acceleration, I'm going to differentiate this velocity one more time, and if I do that, that's a double derivative of your position, and then I'll get x double dot I plus y double dot j plus z double dot k. That's what for acceleration I'll get. That's what we do ijk for rectangular components. Now let's assume that same point traveling the same path in a different coordinate system. So this is the same point, but now we are using polar coordinate system. So we have, instead of x, y, z, we have r, theta, z. So r, theta, z, these are the components instead of x, y we are going to use. And we are going to have ur, u, theta, u, z instead of I, j, k. So if I want to find out position, this particle is moving if we freeze time, and if I want to find out position, rp is given by rur plus zuz. That's how we can define the position. The velocity is the derivative of this r, dr by dt, and so velocity will become vrur, v theta, u theta, vz, uz. These are the velocities, just like we did in x velocity, y velocity, z velocity. Similarly, this is r velocity, this is theta direction velocity, and this one is z direction velocity. Now, without going much into deep mathematics or detailed mathematics, I'm going to give you direct definition of Vr, V theta and Vz. Those are respective velocities. Vr is given as r dot, V theta is given as r theta dot, and Vz is given as simply z dot. These are important definitions. Again, don't worry much about mathematics here, just understand these definitions. Vr is equal to r dot, V theta is equal to r theta dot, Vz is equal to z dot. So this theta dot is nothing but angular velocity. So here this r dot we have r direction velocity. Here this theta dot is angular velocity. Theta is angular displacement. Theta dot is how fast it's rotating. That's your angular velocity. So these are the definitions for velocity. Now if I want to know acceleration, the way we had x double dot I, similarly for acceleration, we are going to have AR UR plus A theta U theta AZ UZ. That's your acceleration for this particle in polar coordinate system. And again, without going much into deep mathematics or detailed mathematics, I'm going to give you definitions for AR, A theta and AZ. So AR is given as R double dot, that's double derivative of R, whatever the position we have here, the double derivative of that, minus R theta dot, that's your angular velocity, into R actual value of R. Then A theta, this acceleration in theta direction, R theta double dot plus 2 R dot theta dot. That's the definition. Again, this theta dot will angular acceleration, how fast it's rotating, and that's your angular acceleration, theta double dot, or double derivative of your angular displacement theta. And then if it is z direction, then that's your z double dot. And these are the definitions that we use to calculate accelerations in radial and theta direction. So this one is in 3 dimension. If most likely we are going to use 2-dimensional polar coordinate or cylindrical components. So in 2 dimensional we only have r and theta, we don't have to worry about z, and if that's the case, the velocity in 2 dimension will become Vr ur V theta U theta, and these are the definitions. And acceleration will become AR ur plus A theta U theta, and these are the same definitions that we are going to use to calculate Vr, V theta, AR and A theta. This is important part. Most likely you have to calculate these things, these 4 things, to get your velocity and acceleration. So let's directly jump to the problem. This is a very interesting problem. Pay attention. So what we have in this problem is a ball being pushed by a rod to move along the slot. So there is a ball here we have, and it's going to be being pushed in this slot by a rod. So this rod is there like this, let's say, and then from here is going to rotate like this, and it's going to continue have this rotation. So what's going to happen as it rotates, it's going to push the slot linearly. So the rod has angular motion, but this ball is going to have linear motion this side. The velocity at which it's going to rotate is given 0.8 radian per second. That's theta dot, or d theta by dt. That's your angular velocity. Whenever you have theta dot, it means it's your angular velocity. So it says 0.8 radian per second. Now you know that this pi radian is 180 degrees. 1 radian is 57 degrees. 0.8 radian is roughly 50 degrees. It means what is happening is 0.8 radian per second means this thing is rotating first 0 time, then in 1 second it's rotating 50 degrees, and 2 seconds is rotating 100 degrees close. So that's the velocity, 0.8 radian per second. So velocity of angular velocity of rod is given. Determine the velocity and acceleration of ball. So it's going to rotate, angular velocity we know. What is the linear velocity of the ball? How fast this ball is going to travel in this part. So at 30-degree angle. So what's going to happen is that from 0 degree it starts moving, it's going to continue to move, but it will reach at 30 degrees. And if you freeze time at 30-degree angle, at that instant, what is the velocity? The motion will continue, the ball will continue to go forward, but at that instant, the 30-degree mark, what is the velocity of the ball and what is the acceleration? That's what we have to calculate. That's the problem. Now, to calculate that, as this is rotating, I'm going to use cylindrical components. I'm going to use UR and U theta. Whenever you have rotation, you use polar coordinate system. So we are going to use ur and u theta. So what I am going to do is that to calculate the velocity of this ball, I am going to calculate the velocity, the point which is connected to this ball on the rod. Whatever the velocity of that point at that instant of this point will be same equal to the velocity of the ball. So that's what I'm going to do. I'm going to mark a point, and for that point I'm going to calculate the velocity and acceleration. And then that point I'm going to drop the point, and then I'm going to say this one is ur and this one is u theta. So that's your r and theta component with respective coordinate system. So this is my 0, 0 point coordinate system, and then it's going to move like that, and then this is my r and this is my theta direction. So here I have ur, here I have u theta, and then this theta will become 30 degrees, and at that instant I want to calculate. Now what does it mean? So when it comes here at this point, this is the velocity for the ball. It will have two components here, vr and v theta. Just like we have x velocity and y velocity, I am going to resolve this v velocity into two components, vr velocity and v theta velocity. And combination of these two velocities will be my velocity for the point, velocity for the ball. That's what we are going to do. Same thing with acceleration. I am going to resolve the acceleration of that point into two components, r component and theta component, ar and a theta. So combination of ar and a theta will give you me acceleration. So that's the game. What we want to do in this problem is to calculate Vr, V theta, Ar, A theta. Once you have that, we use Pythagoras. Vr, V theta, we can calculate velocity of the point, velocity of the ball. Here we calculate Ar and A theta. We calculate acceleration of that point and acceleration of that ball. So that's what we do. We calculate this, and then we'll get the value of V and V. So in this problem, we have to calculate four values: Vr, V theta, Ar, A theta. Just like you calculate x velocity and y velocity, similarly r velocity, theta velocity, r acceleration, theta acceleration. That's what we are going to calculate in this problem. Okay, so let's get on it. Now, in this problem, here the definitions we have is this one. We have Vr is equal to r dot. We know that. We did it earlier. That's the definition we are going to use. And V theta is equal to r theta dot. Our objective is to calculate Vr and V theta. So if we can calculate value of Vr by using this r dot, and then V theta by using r theta dot, we should be able to find Vr and V theta. That's the goal. So how to get that r dot? What is r dot? What is r here? R dot is nothing but dr by dt. But what is r? First, we have to find out. So, if you look at this diagram, what we are going to do is that we are going to draw a right angle triangle here. This one, this one, this one. So this is my right angle triangle, and theta is 30 degree here. So, in this right angle triangle, you can see this one is r, is given here. This slide is 0.2 meters, this theta is 30 degree. So, if I want to have definition of the r, then I can say cos theta is equal to 0.2 by r. So, this is the right angle triangle, and that's what I am going to write here. Cos theta is equal to 0.2 by r, and this is important. Most people get confused, where does the r come? So keep that in mind. Cos theta is 0.2 by r based on your right angle triangle. Then the value of r will become r is equal to 0.2 by cos theta. So here, based on trigonometry, cos theta is 0.2 by r becomes 0.2 by cos theta. Or I can rewrite this value of r as 0.2 sec theta. 1 over cos is sec. So I am going to simply write down as 0.2 sec theta. That's the value of r I get. 0.2 sec theta. Now, to get dr by dt, the velocity, the dr by dt, I need to find out derivative of this 0.2 sec theta. If I get that 0.2 sec theta, derivative of 0.2 sec theta, I can get r dot, and that is nothing but Vr. That's the first value here. That's r component. So that's r component. Yeah. So here, now to get that, to find the derivative, I am going to do r dot as dr by dt is equal to 0.2 d sec theta by dt. Now here, what we have is theta here, dt here. You cannot have direct differentiation here. We have to use chain rule. So for that, what I am going to do, to find the derivative of sec theta with respective time, I am going to multiply and divide this one by d theta. So that's what we do here, 0.2 d sec theta by d theta into d theta by dt. So you multiply and divide this thing by d theta. And if you do that, now you can find out the derivative of sec theta. And d theta by dt is nothing but theta dot. That's your angular displacement. The value of theta dot is already given. That's d theta by dt, 0.8 radian per square. That's your velocity. Angular velocity is given here. So this is theta dot. Derivative of sec theta is sec theta tan theta. So this entire thing becomes 0.2 into sec theta, 0.2 into sec theta tan theta into theta dot, and that will be this one. So 0.2 sec theta tan theta, theta dot. Now once you have this r dot, what you do is that put theta is equal to 30 degree in this problem. So 0.2 into sec 30 into tan 30 into 0.8. That's what you do. You put the values in 0.8, 30, 30 here, all that. You put that here, and then you can calculate r dot. And if you do that, you will get r dot as 0.106 meter per second. That's the value you get. 0.2 into sec 30 into tan 30 into 0.8. You do that, do those calculation, and you will get value of r dot. It means that now you have value of Vr. Once you have value of Vr, V theta is easy. V theta is only r into theta dot. R is this one, 0.2 sec theta. You got it from the trigonometry. 0.2 sec theta, it means 0.2 sec 30. That's your r. So I'm going to put that 0.2 sec 30 here, and then once I do that, I'll get r. Theta is 0.8, so 0.2 sec 30 into 0.8 will be my V theta. And if I do that, V theta I will get as 0.184 meter per second. So these are the r velocity and theta velocity I will get. Once I have these two components of velocities, I can calculate this V. I am going to put Vr here, V theta here, and then I can calculate V as 0.213 meter per second. That's the velocity I'll get. It means that that's what the velocity of this point, that's what the velocity of ball is moving in this direction. So that's the problem. Get the value of Vr, get the value of V theta, get the velocity. First, to get r from the trigonometry, we got r as 0.2 by, cos theta is 0.2 by r, or r is equal to 0.2 sec theta. Find the derivative of r, get the r dot, and do the calculations, get Vr, V theta, get the velocity. That's the problem. That's the first part. Now we have to find out this acceleration. To find out acceleration, we have these definitions. Acceleration definition for acceleration is r double dot minus r theta dot square, and r theta double dot plus 2r dot theta dot. Now, here r dot is double derivative of r. So we have already r. Remember we already calculated r as 0.2 sec theta. We have the value of r. Now we have to find double derivative of that. That's your r double dot. We need to differentiate with time 2 times. So, and then this one r is 0.2 sec theta. Theta is 30 degrees. You can theta dot is 0.8. You can calculate that. You will get the value of ar. And a theta here, this theta double dot. Theta double dot means angular acceleration. Now angular velocity is constant, it's not depend on time. So angular velocity is constant 0.8. It means that angular acceleration is 0. Derivative of constant is 0 as velocity is constant. This is rotating with constant angular velocity. And if that's the case, angular acceleration is 0. It means theta double dot is going to be 0. So if it is 0, all I have to do is calculate only this value 2 r dot theta dot. I can calculate r dot, I already did. We already calculated r dot. We have theta dot 0.8. 2 r dot theta dot will be a theta. So a theta is very easy. We have to find out this one, a r double dot. Once we calculate r double dot, we should be able to calculate this a r. That's your r component of acceleration and theta component of acceleration. Thus, just the way you have x component and y component, in this problem we have r component and theta component. You calculate those, you can get AR and A theta, you will get it. Okay, the final acceleration. So let's start with this one, r double dot. First we have to find out this r double dot. So last time we already did r dot dr by dt is 0.2 sec theta tan theta into theta dot. We already have r dot. Now we have to find out the derivative of this r dot one more time. It means differentiate it with time one more time. That's dr dot r double dot is equal to dr dot by dt. That's what we want to find out, dr dot by dt. So to do that, to find the derivative of this one, we are going to put this 0.2 number as a constant, so it is outside the bracket. And this one I'm going to use, there are three terms here, sec theta, tan theta and theta dot, which is nothing but d theta by dt. The derivative of this one I'm going to use product rule. Product rule means I'm going to get the derivative of one thing and then keep other two constant, plus derivative of other thing, keep the other two constant, so on and so forth. So you know the product rule. So in this case, first part I'm going to get this tan theta dot constant and derivative of sec theta d sec theta by dt. Then I'm going to put this sec theta and theta dot constant and in derivative of tan theta by dt, and then I'm going to put that sec theta tan theta constant, and then I'm going to get derivative of theta dot, only this one. This term will become d theta dot by dt is nothing but theta double dot, that is angular acceleration. Angular velocity, derivative of it will be angular acceleration. In this case, angular acceleration is 0. So this term becomes 0. It means this term, entire term will become 0, and you will see that. Now here I have theta dt here. So I can't have direct derivative here. So it means that I have to multiply and divide it by d theta. I have to use chain rule. So I'm going to use chain rule here. I'm going to use chain rule here, and if I do that, I'll get something like this. 0.2 tan theta dot stays same. This one divided by d theta multiplied by d theta. So d sec theta by d theta by dt. And that is nothing but theta dot. Same thing here, d tan theta by d theta by dt. This is nothing but again theta dot. That's your angular velocity. And this one stays same. I'm not going to do anything with this one because this is going to become 0 anyway. D theta by dt will become theta double dot. So this will become 0. All I have to do is solve for this one. This theta dot here will become theta dot square. Tan theta will stay same. Derivative of sec theta will become sec theta tan theta. So they will get derivative of that. Same thing here. We'll solve that. This theta dot and this theta dot will become theta dot square, and then I'm going to have derivative of tan theta is nothing but sec square theta. So this one sec square theta and sec theta will become sec cube theta. So let's calculate that derivative, and if you do that, you will get something like this: 0.2 into sec theta tan square theta dot square. Why? This one and this one, that square. Sec theta will become tan theta. So sec theta tan theta, and they will become tan square theta and sec theta. So sec theta tan square theta dot square plus sec cube theta. So here derivative of tan theta is sec square and sec theta will become sec cube theta. So sec cube theta dot square. This theta dot and this theta dot will come together and will become theta dot square. That's the r double dot you get. That's the value of these r double dot. Once you do that, this looks complicated, but this is really not. If you know your calculus, this is easy. Try it slowly, try it one by one, do more practice, you will get that. So now what we have here, put theta is equal to 30 degrees. Theta is equal to 30 degrees. 0.8 square sec cube 30, again 0.8 square. You do that and you will get final number as r double dot is equal to 0.246 meter per second square. That's what you get, r double dot. Once you put the values here, you will get the value for r double dot. Once you have r double dot, all you have to do is get that r double dot here, put in here, minus r, you already have value of r last time we calculated 0.23, into 0.8 square, you will get value of AR. And same thing, this becomes 0, r dot we have, theta dot 0.8 we have, we can calculate a theta. So once you have r double dot, rest is easy, you will get a value of AR, you will get a value of A theta. So AR, if you calculate this one, altogether you will get 0.0985 meter per second square, and then you will get A theta as 0.17 meter per second square. That's what your R component and theta component. Once you have these two components, put them here, then you will get acceleration. So final number for the acceleration will come as 0.19 meter per second square. It means that this one is rotating, this point has an acceleration of 0.19 meter per second square, and that's the problem. So that's the final answer. Now you have velocity and now you have acceleration. So that's how you can solve this problem, by using this r and theta component. So this is very important problem. Do more practice and you will get there. Now let's move on to the next part, absolute dependent motion analysis of two particles. So far we are dealing with only one particle or one object. Now what to do if we are dealing with two objects simultaneously where the motion is dependent? For example, here we have point A and point B, or object A, object B, or particle A, particle B, and then they are connected with one rope. So now you can imagine if this A goes up, B will go down, or B goes up, A will go down. You can imagine that, and the velocity will stay same. It dependent, A, the velocity of A is dependent on B, or you can say B, velocity of B dependent on A. And then for this problem you can imagine whatever the velocity of A will be velocity of B in opposite direction. If this is going upward in 2 meter per second, this will come down with 2 meter per second. So we know the velocity will be same in opposite direction. But how to calculate velocity? Something like this. So here we have two objects or two particles, and then we have three pulleys, we have two different ropes. There is no direct connection like this, so they are connected indirectly. Unlike here, this A is going to go up, B is going to go down, but at what velocity? It's not going to be same. At what velocity? Or B goes up, A will come down, at what velocity? We want to find out that velocity relationship between A and B, and that's the whole problem. Okay then. So to solve this kind of problem, absolute dependent motion, we follow some steps. 5 or 6 steps are there altogether. We have to follow them. So first of all, whenever you have this kind of problem, start with step 1. Step 1 is set up your coordinate system. It's very simple step. What you do is that whatever fixed pulley you have here, this one is at the top, I'm going to draw a line and then I'm going to call it a datum. And that's the step 1. Draw a coordinate system O. And then I'm going to say all the distances, all the velocities downward will be positive. It means the velocity, if this is going downward, that velocity is positive. If this is coming upward, that velocity is negative. So from the datum, I'm going to measure all the distances, and downward is my positive. That's what I'm going to set for the step 1. Once you are done with the step 1, then step 2 is represent the positions of A and B. So I have this datum here. From that, the step 2 is that I'm going to mark a position SA and SB. So SA is the distance from the datum of particle A, and SB is the distance from particle B from the datum. So SA, SB, that's the step 2. Remember, downward positive. Recognize the constant length. Throughout this process, what's going to happen if A goes up or B goes down, this SA and SB will change. The length, this length will change as it goes up and down. However, this length is going to stay constant because the circumference of this pulley is constant, so half of whatever it is, L semi, so that's going to stay constant, and whatever happens, the rope length of entire rope is going to stay constant from this point to this point. So keep that in mind. There will be always some constant length, so and recognize that. So here L semi is constant length, and that's the step 3. Recognize the constant length. Then the most important step in this problem is step 4. In step 4, what you have to do is to write the equation for entire rope, entire length of the rope. It means the total length of the rope in this case is equal to SA plus L semi, that is a constant length, plus SB, that's my total length. So that's what I am going to do, step 4. SA plus L semi plus SB is equal to total length. That's the equation. And all you need to do is get this equation right. Now, of course, this one is simple, but later you will see complicated problems. If you get this equation right, you solve 80% of the problem. Get this one right. SA plus L semi plus SB is equal to total length. You're done with your total length. Recognize the constant length again. L semi and LT are constants. Keep that in mind. So they are going to be our constant lengths. Now, you go to step 5. You have your equation for entire row. In step 5, what we do is we differentiate this thing with time. This equation, I am going to differentiate it with time, and if I do that, it will look something like this. So derivative of this thing with time is equal to derivative of total length with time. Derivative of constant, derivative of L semi and derivative of LT is going to be 0. Derivative of constant is 0. So I'll get the equation as dSA by dt plus dSB by dt is equal to 0. dSA by dt is nothing but velocity of particle A, and dSB by dt nothing but velocity of particle. That's your distance upon time, ds by dt. So that's a change in distance of SA with respect to time. That means that you have velocity of A plus velocity of B is equal to 0. VA plus VB is equal to 0, or I can rewrite it as VA is equal to minus VB. That's it. That's the problem. VA is equal to minus VB. Now it means that you know whatever the velocity magnitude is going to stay same, direction will be opposite because of the minus sign. That's how we can do this one. That's your velocity. If there is an acceleration is asked, if you want to know how fast they are going to accelerate, then whatever you got the equation VA is equal to minus VB, you are going to differentiate it one more time with time. And if you do that, you will get acceleration AA is equal to minus AB. And that's it. That's how you can calculate acceleration. Let's do one more problem. Let's see if we can get the velocities by using these steps for this kind of problem. Now in this problem, what we have is we have two particles, particle A, particle B. We have 3 pulleys and we have 2 ropes. One is orange rope and one is here another blue rope I have here. So this A is going upward in 3 meter direction. We want to find out how fast B is going to go down. What is the velocity of B? Or we want to find out the velocity relationship VA and VB. What is the relationship between them? That's the problem. So we start with our step 1, set up a coordinate system. Here I'm going to set up my coordinate system here, datum, and then all the distance is downward positive. The S is positive. That's the step 1, get the datum. Step 2 represents all the positions. So position of A, position of B from the datum, represent that. So that's what I'm going to do. SA downward, SB downward, and this pulley is also going to up and down, is going to move. So I'm going to mark this pulley as a C, and this is also downward. That's the distance of pulley C, point particle A, particle B. Mark it down. Step 3. In step 3, recognize the constant length. This one is going to constant, this one is constant, this one is constant, 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 and total length is going to stay constant. Recognize the constant length. Step 4, most important step. In this problem, what we have is 2 ropes. orange rope and blue rope. So we have two ropes here. It means we are going to have two equations. One equation for this rope, another equation is for this rope. That's the equation for entire rope. That's the step 4, most important step. So here I am going to say first equation is equal to SA plus constant length plus SC plus constant length plus SC plus constant length is equal to total equation. So I am going to write down that equation. It will look something like this. SA plus SC plus SC is equal to C1. All that constant I am going to club it together and I am going to call it C1 is equal to LT1. That's my total length. I'm done. SA plus SC plus SC plus C1 is equal to constant length. Now I'm going to go with this part. Second rope. Now second rope I have SB and this length. Now many students get confused about this part. So here what I'm going to do, this section I'm going to consider it as a part of a rope. Okay, so keep that in mind. This section here of the pulley I'm going to consider it as a part of a rope. It means that I'm going to calculate this length from this point to this point. So this length is nothing but SB minus SC. So if I subtract this SC from this SB, I'll get this length from point C to this point. And that's the total length of this rope. So here that will become SB minus SC, this length plus SB, this length plus whatever the constant I have there, that's C2. So SB minus SC plus SB plus C2 is equal to LT2. All you need to do in these problems is get these equations right. If you can get this equation right, these problems are very easy. If you don't understand it, if you get confused because of this like this, you won't get it right. So keep that in mind. Do a lot of practice, it will be easy. Get this if length right. Once you have these two equations, all I have to do is eliminate SC. In this case, I don't need velocity of C. All I may care about velocity of A and B. I have to find out, eliminate SC. I have two equations, so I'm going to equate them. So I have SA plus SC plus SC plus C1, this one. So here I have 2 SC, I have 1 SC here. I'm going to multiply this equation with 2. So this SB will become 2 SB, multiplication will become 4 SB. 4 SB minus 2 SC plus C2 is equal to 0. So this will become plus 2 SC here, SA plus 2 SC plus C1 LT1, and this will become 4 SB. I'm going to multiply it by 2, so this will become 4 SB minus 2 SC plus 2 C2 plus 2 LT2. So that's the equation will become, that's your second equation, 4 SB minus 2 SC. So here I'm going to equate these two equations, plus SC plus 2 SC minus 2 SC will cancel it. And then all these constants, C1, C2, LT, I'm going to club it together and I'm going to write down one equation for everything. And that will become SA plus 4SB is equal to L constant. So all the constants clubbed together, that will become L constant, SA plus 4SB, and that's what we are looking for. Once you get there, 90% problem is solved. SA plus 4SB is equal to L constant. That's your relationship between particle A and particle B with respect to distance. Now, step 5 is easy. Differentiate that equation with time. It is very simple. dSA by dF4 dSB by dt is equal to L constant. That's your velocity for A. That's your velocity for B is equal to 0. That will become VA plus 4VB is equal to 0. Now you have relationship VA is equal to minus 4VB. All you have to do is that put VA3 here. Now in this case, this 3 is going upward direction. So when it does that upward direction, I am going to put that VA as a minus 3. This will become minus 3 is equal to 4. Or I can take this VA here. That will become minus VA, minus 3, minus become plus 4 VB is equal to 3. VB is equal to 3 by 4. And therefore VB will become as 0.75 meter per second. So this A is going upward with 3 meter per second. B is coming downward with 0.75 meter per second. You can write like that, or you can represent a direction, downward direction later, and then that's how you can solve this problem. So ultimately, the only thing in this problem you need to remember to get these equations right. Once you have equation, differentiate with time, get the relationship between velocities, you are done with the problem. And that's how you can solve this one. There is a problem, I'm going to put it This one is a solved problem from the book. So here, for this kind of problem, if you go on example 1223 on page 89 of your book, you can find this problem. This one is very easy. You have to do this, follow the same process. You have to get the equations for these two ropes, and then you can solve this problem. This one is very easy problem. Go on page 89, 1223, and then you can solve the problem. There is another problem here. In this problem, it's the same problem, again same process. In this problem, there is a one rope that we are using. This point B is going to come down with 4 meters per second, and then as it comes down, you can imagine this A will go in upward direction. We want to find out velocity of A. So we will go to the problem quickly. Select a datum for this problem. Once you select a datum, mark the position. That's your step 2. SA, SB, SC. You mark the position, and then you recognize the constant length. So here, this length is constant, this length is constant. For this particular problem, this point C is connected to this pulley, so this length SC is going to be constant. So keep that in mind, SC is constant. Our objective, B is coming with 4 meters per second, A is going to upward. We're going to find out how fast is A is going to go upward. So now, fourth step, most important, write down the equation for entire rope. We have one rope, we are going to get one equation. Here, the equation will become SB plus constant plus SA plus this length. Now in this problem, I'm going to consider this length as a part of a rope. So I'm going to consider this length and this length as the same size. So keep that in mind. This length and this length will become SA minus SC. So SA minus SC will become this length. So here this length and this length is going to stay constant, and this one is SA. So SA into 2 into bracket SA minus SC, this length and this length. So I'm going to write that equation down. SA, this length, plus SB, plus this length and this length, they are same. So 2 SA minus SC, L constant. You write that down. You get this equation right, the problem is easy. 3 SA plus SB is L constant. So that's SA into 2 SA, 3 SA. SB, SC is constant. So I'm going to take that SC. This SC is constant. So I'm going to take that here. That's the equation. I'm going to differentiate this equation with time, and if I do that, I will get 3VA plus VB is equal to 0. That's the relationship. So all I have to do is that put 4 here and then calculate VA. So VA is positive 4 here, VB is positive 4 here, VA will become 4 by 3, and that's VA will become 4 by 3, that will be negative minus 1.33 meters. So that's the answer you are going to get, or VA 1.33 meter per second upward. That's the velocity of A. Again, most important part of this problem is to get this equation right. If you get that, you can solve this problem. It's very easy. Now let's do a final part of this chapter, relative motion of two particles. So far in this type of problem, the motion was dependent on one and another. So what to do if there are two particles, they are not dependent in motion, but they are both are moving? How to calculate that relative motion? So you are also moving, your friend is also moving, both have very different directions. How to calculate relative motion between these two particles? So that's your relative motion between two particles. So let's assume that there is a duck swimming in the pond with very small velocity, 0.5 meter per second, let's say. So it's swimming in the pond or a river, and then there are you are watching that duck. You are stationary, you are not moving at all. So you are stationary, and then there is your friend. He's also moving in the same direction as duck is moving. So he has velocity, let's say 1 meter per second. So he is moving with 1 meter per second, duck is moving with half meter per second. You are stationary. Here we want to find out, as these two things are moving, let's call him A, let's call duck B. A and B, particle A and particle B are moving. We want to find out relative velocities and relative acceleration between A and B. That's what we want to do here. Now to do that, maybe we want to find an equation for that. Now to do that, as you are stationary here, I'm going to set up my coordinate system on you. So here you are stationary, that's my coordinate system, x, y, z on you. That's I'm going to call it as fixed reference frame or fixed coordinate system, because you are stationary. And then as these things both are moving, they have magnitude and direction, I'm going to draw a position vector from your friend position vector RA, and from B position vector RB. So it has magnitude and direction. That's the position vector. Then as your friend is moving, I am going to draw another. Now my objective is to calculate the velocity of duck, velocity of B with respect to A. So as he is moving, I am going to draw a translating frame, another frame, but this is not fixed. This one XYZ axis is moving. That's what we call translating frame. Translating is mean moving in one direction. It's not rotating. It's translating. So I am going to draw another section here. And then from A, the position of B will become RB by A. Position of B with respect to A. R is my position vector. Both are moving, both have directions, both have magnitude. So RB by A. So here RA, RB and RB by A are vectors. And if you know vector law or vector addition rules, then you can say this RB by A is equal to RB minus RA. RB by A, position of B with respect to A is RB minus RA. That's what the equation I will get. And now that's the relationship between positions of B and A. Now if I want to know velocities, so this one is a position. If I want to know velocities, I'm going to differentiate this equation with respect to time. And if I do that, I'll get VB by A is equal to VB minus VA. That's the relative velocity. If I want to know acceleration of B with respect to A, then I'm going to say acceleration of B with respect to A is AB minus A. I'm going to differentiate this equation with time, and then I'll get acceleration. So that's how you do relative motion of two particles A and B. You will get position, differentiation, time, velocity, you'll get acceleration. And these are the formulas that we use to calculate velocity and acceleration. That's relative velocities of and acceleration of any two particles. Let's jump on directly to the problem. Now in this problem what we have is two particles. Two particles, A is moving with 4 meter per second and it has some acceleration of 10 meter per second square, and B is moving also in this direction 8 meter per second. Now when you have relative velocities, if let's say you have two trains going in same direction, then you can calculate relative velocities relatively easily. But this kind of problem here, this is taking a turn and it has completely different direction. This B is going in this direction. They are completely different direction at different velocities. So we have to find a way to calculate relative motion between them, relative velocity and relative acceleration. So it says that A moving with 4 meter per second with acceleration 10 meter per second square, it's rotating at 0.5. As it is rotating, it has two components of acceleration, normal and tangential component, this one. And this B is going in this direction, this is a straight line. This B is decreasing in 0.5 meter per second. So this one is going in this direction, but the velocity is going down with 5 meter per second square. That's negative acceleration. Find out relative velocity and acceleration of A with respect to B. It means that we have to find out VA with respect to B, velocity of A with respect to B, and acceleration of A with respect to B. That's the problem. So for the first part, the first thing that we do in this kind of problem is set up our coordinate system X and Y. So I'm going to regular set up X, Y and Y coordinate system. So I'm going to get that because it has magnitude and direction, I need to use I and J vectors. So X and Y I'm going to set up, and this A is going in this direction, that's Y direction. And this B is going in this direction, that's negative X direction. So I'm going to keep that in mind. So velocity of A becomes 4j meter per second. That's velocity has magnitude and direction. J is used for I direction. It's a unit vector. I and J. J is for Y direction. So that's my 4j. VB is equal to minus 8i. This one is going into X direction. That's negative X direction. It will become minus 8i meter per second with magnitude and direction. Once I have VB, I have VA. That's their absolute velocities. Now the relative motion is velocity of A with respect to B is VA minus VB. That's the formula. You do put those things into this formula, you will get relative velocity. So now I'm going to put them into formula. I'll get relative velocity as 8i plus 4j. So this one is minus 8i, minus minus will become plus. So that will become plus 8i. So I'm going to write that down. Plus 8i plus 4j is meter per second. It has magnitude and direction. If I want to know just magnitude of that velocity, I'm going to put this into Pythagoras. I will have VA square plus VB square and I'll get V. That's the magnitude between relative velocity magnitude, and that will become as 8.94. So 8 square 64 plus 4 square, which is 16. So 64 plus 16 under root, whatever it is, you will get under root 80.894 meter per second. So relative velocities at that instant between these 2 points is 8.94 meter per second. That's the first part. Second part, find out acceleration. For acceleration, as this is taking a turn, it has 2 components, an and at, tangential component and normal component, because it's taking a turn. So tangential component increasing in 10 meter per second, so that will be 10j. So it's increasing in this direction, that will be 10j meter per second square. And then there is a normal component, as it's taking a turn, is VA square by rho. Velocity is 4, rho is 0.5, 16, 4 square is 16, 16 by 0.5, it will become 32. So that's my 32i. Normal component is in this direction, that's positive x, that's why I will use I. 32i meter per second square. At and an, once I have at and an, the collective acceleration altogether I can write it as 32i plus 10j meter per second square, and that's the acceleration for particle A. Then for particle B, it says 5 meter per second decreasing. Particle B is slowing down. Particle B has negative acceleration of 5 meter per second square. However, particle B is moving in negative x direction. So that's negative x and negative 5 become positive, negative become positive, and then I'll get positive 5i meter per second square. That's acceleration of B in this direction. So acceleration of B is 5i, acceleration of A is 32i plus 10j. Now the relative acceleration between two, I have a formula. Acceleration of A with respect to V is A minus AB. I'm going to put these numbers in the formula, and then I'll get final acceleration as 27i plus 10j. That's it. Once I have that, I'm going to put that. This one is magnitude and direction. Just magnitude of the acceleration between these two will be 27 square plus 10 square under root, and then you should get answer around 27.79. I think this one is 28/79. So this one is typo probably. So that's the answer you will get, 28 plus 79 meter per second square. So that's how you can do these problems. So that's the final part of this chapter. These are some practice problems I'm going to put there. So they are there on Blackboard, so just practice them, and that's pretty much chapter 12. This chapter, most important part of this chapter is make sure that you understand those kinematic equations that we derived in first video, and make sure that you understand how the coordinate systems work. The rectangular coordinate system, cylindrical component, polar coordinate system, and normal and tangential component. This chapter 12 is the foundation of dynamics, whatever the chapters we are going to study. So keep that in mind. We'll stop here now. Next video we'll start our particle kinetics, that's force and acceleration. Alright then, stay safe, have a good day.